Hey guys, what's up? Today we are going to look at a method of solving the heat equation using an integral method. I'm called also Derek. Let's continue. In this slide, the heat equation is stated as shown there. The boundary conditions are also given. The boundary conditions are T is equal to Ts at x is equal to 0 for all t, T is equal to T infinity at x is equal to infinity for all t, and the initial condition is T is equal to T infinity at T is equal to 0 for all x. Let's continue. Now, to solve the heat equation, we postulate a temperature profile that will satisfy the boundary conditions. And an exponential temperature profile will satisfy the boundary conditions. You can go ahead and prove this. Now, for the initial condition to be satisfied, we assume that lambda, which is a function of t, will be in the form given below. In other words, lambda is proportional to the time t. That's what we assume. So that at t is equal to 0, lambda will be equal to 0, and the initial condition will be satisfied. Now the next step is transforming the PDE into an integral equation. You notice that the heat equation is now being integrated with respect to x from 0 to L, where L is the length of the rod. You notice that the integral to the right, given by dt dx from 0 to L, this integral can be given by the dt of t minus t infinity dx from 0 to L. This can be verified since L and t infinity are constants independent of time. Now the heat equation is now given by the second derivative of temperature with respect to x from 0 to L dx and thermodynamicity is equal to the dt from 0 to L of t minus t infinity dx. Let's continue. Now using the exponential temperature profile we postulated, we go ahead and find the integral of the second derivative of temperature with respect to distance x dx from 0 to L as negative ts minus t infinity over lambda, open brackets exponential negative L over lambda minus 1. We also go ahead to find the integral of t minus t infinity dx from 0 to L as equal to negative lambda ts minus t infinity exponential negative L over lambda minus 1. Now we go ahead and substitute these expressions we've got into the integral equation, and we end up with a differential equation whose boundary conditions are lambda is equal to 0 at t is equal to 0. We finally get the solution as lambda is equal to square root of 2 thermodynamicity times t. Let's continue. Now we go ahead and substitute the value of lambda got into the temperature profile we postulated and get the temperature profile given by t minus t infinity over ts minus t infinity is equal to exponential negative x over square root of 2 thermodynamicity times t. Or we can modify this temperature profile into another form given by ts minus t over ts minus t infinity is equal to 1 minus exponential negative x over square root of 2 times thermodynamicity times t. Now you notice that we postulated that for the initial condition to be satisfied, lambda should be proportional to t. And that's what we have got. If you go ahead and substitute the time t is equal to 0 into this temperature profile, you will get the initial condition. So since the boundary conditions and the initial conditions are satisfied, we've solved the heat equation. Thank you.